Hello everyone, I'm Nobuo Hashimoto, a student in the Department of Computer Science in the University of Tokyo. I'm now researching video image processing and FPGA. I believe you all agree that there is a room for further acceleration in video image processing on FPGA. So today, I would like to explain how to design a complex depth estimation algorithm on FPGA using hardware-software co-design. First of all, I'd like to introduce the backgrounds of depth estimation, and then I will explain how to design the proposed accelerator FADEC. Then we will look at the experimental results on an actual FPGA board from qualitative and quantitative perspectives. And finally, we will conclude our presentation. So we will move on to the background section. First, let me give you a brief explanation of depth estimation, which aims to estimate the distance between the camera and the target objects. This task has attracted attention because of its wide range of applications, including navigation for autonomous driving and AR. However, this task often requires a complex algorithm that combine traditional image-video processing algorithms and DNNs. Basically, the mechanism is similar to our eyes. We obtain the output depth map from input 2+ images, like the figures below. Firstly, we use a stereo matching principle to find the corresponding points in the 2+ images that capture the same target object. Then we will use a triangulation principle to geometrically calculate the distance between camera and target objects in each pixel, using corresponding points and camera poses as input. However, finding accurate corresponding points in 2+ images based on degree of similarity is difficult, so there are a lot of DNN-based algorithms. Among them, we chose DeepVideoMVS, which has three following features. 1. It can estimate depth map from simple inputs, video from monocular camera and camera poses of each frame. 2. It can be applied to a wide range of situations without training again to adjust each scene. 3. It is likely to operate at near real-time speeds in low-power embedded environments. Then we explain the DeepVideoMVS. The diagram of the DeepVideoMVS is as follows. First, we show the DNN-based processes in blue squares. The image features are extracted from input frames using an encoder-decoder network of CNNs. Then we obtain cost volume, which shows the degree of correspondence between points in each image. The cost volume is arranged using CNNs again to obtain the output depth map. Here, thanks to the RNN in the middle, we can make use of the previous depth map information. DeepVideoMVS processes time series information in this way to improve accuracy. Then we show the traditional image-video processing in red squares. The keyframe buffer stores the past frames to reuse the frames with a similar pose to the input pose. Selected frames are used for stereo matching. In the cost volume fusion and hidden set correction, the grid sampling is performed to apply viewpoint changes. Although the combination of these processes and DNN-based processes can improve accuracy, it makes acceleration more difficult. Then we explain our proposed accelerator FADEC. We design FADEC in the following flow. First, in the hardware-software co-design, we determine software-friendly processes by taking advantage of characteristics of hardware and software, because not all processes are suitable for hardware implementation. Next, in the hardware design, we design custom circuits for the hardware-friendly processes on PL using an open-source high-level synthesis tool called NNGen. The hardware architecture is shown here. The circuit uses a state machine to automatically control the operations like comb and upsampling. The necessary operations are performed in order from the front. Then we designed optimized programs for the software-friendly processes on CPU so that it can be executed upon request from PL. Finally, we hide execution latencies of hardware and software implementations by executing them in parallel on the PL and the CPU. Now, we will explain one for design and for scheduling in detail. In hardware-software co-design, we consider the number of executions, characteristics, and memory access pattern of each process to determine operations to be implemented in software. We can hide the execution latencies of these processes by executing them in parallel with hardware-friendly processes. Operations in red squares in the right figure are software-friendly processes. The blue squares indicate the correspondence between each process in the diagram and in the table. The grid sampling performs bilinear interpolation to obtain the value at the position represented by the coordinates specified for each element. As this operator requires irregular memory access, accelerating it by hardware is difficult. It also has the largest latency among software-friendly operations because multiplications are performed many times. Thus, hiding the latencies of the grid sampling is the most important. In the hardware-software scheduling, we hide the execution latencies by making the PL and the CPU work parallelly and cooperatively. Here, we require communication mechanism between hardware and software to notify the end of each process and exchange data, and the task-level parallelization. We realize the communication mechanism by using the CMA and the interrupt handling mechanism. The CMA is used to allocate a contiguous physical memory area. Hardware directly accesses the physical memory, whereas software handles the virtual memory area. So it is difficult to control where in the physical memory software accesses. Thus, we realized the communication mechanism between hardware and software by allocating a contiguous physical memory area in advance and reading-writing data within the area. The interrupt handling mechanism in the right bottom figure shows how to exchange data. When the PL process finishes, the data are written to the memory, and an opcode representing the next CPU process is written to a specific register, and the PL process is suspended. When the CPU detects the opcode by polling, it reads the data from the memory and executes the specified process. When the process is completed, the output is written to the memory, and an end flag is set in a specific register. The PL then reads this flag and resumes the next process. In the task parallelization, we increase the parallelism to hide maximum execution latencies by placing each process in hardware and software properly. The CVF includes the grid sampling, which has the largest latency among software-friendly processes. The data dependency analysis in the CVF reveals that the grid sampling does not require the output of the previous process FS. Thus, we can hide 93% of the total latencies required for the CVF by executing the grid sampling in parallel with the FE and FS. Following this procedure, we complete the accelerator by placing each process properly shown in this figure. Then we explain the evaluation of FADEC. We implement FADEC on an FPGA and compare it with a C++ implementation on CPU on the same FPGA board. Although the input size is small due to the setting of the CMA size, we enable to make it larger without changing the overall architecture. We used the pre-trained model published by the authors of the DeepVideoMVS and Xilinx ZC104 board. We implement the hardware design in Python and convert it to a bitstream using NNJ and Vivado. We used Python instead of Python for the software design, and implemented the design as fast functions callable from Python. We use Pink for execution and 7 scenes dataset for evaluation. The C++ implementation is compiled using C++ with all 3 options and executed on the same FPGA board. Here we look at the execution time and hardware resource utilization. The clock frequency of FADEC is 187.512 MHz. The execution time is 0.278 seconds per frame, which is 60.2 times faster than the CPU-only execution. The utilization of the slices and VRAMs is nearly 100%, which indicates that we can take full advantage of the hardware resources. The left bottom images are the results of qualitative evaluation. Our outputs do not exhibit sufficient degradation to be visually distinguishable. The right bottom graph is the results of quantitative evaluation, which shows scene-by-scene comparison of MSE between outputs of FADEC and C++ implementation and ground truth. This graph indicates that the accuracy is slightly degraded compared to the C++ implementation, but the degradation remains below 10% in most cases. Finally, we conclude our presentation. In this study, we accelerated the complex depth estimation algorithm that combines traditional image video processing algorithms and DNNs. Then we also proposed and implemented the FPGA-based accelerator FADEC for the DeepVideoMVS, using the hardware-software co-design. Finally, we demonstrated that FADEC operates 60.2 times faster than the CPU-only execution on Xilinx ZC104 board with minimal accuracy degradation. Thank you for listening. If you have any questions, feel free to ask me.